little examples that we're going to do in this top little table, and then we're going to talk more about the relationships that exist. So the easiest shape that exists in the entire world is a square. And a square is lovely because it has the same side lengths on every side. And the area of a square is also very easy to calculate because the area of a square is very simply length times width is equal to the surface area. So for this particular square that I've drawn here, it's 1 centimeter by 1 centimeter. In other words, 1 times 1. And that would leave us with a final solution of 1 centimeter squared. That's the actual surface area for that. Let's say that I wanted to scale that up 2 times. Let's say that I wanted a square that was twice as big. What that would then have to look like is when I draw my new square, I'll have to change both of the side lengths by that scale factor of 2. So if the width here was previously 1 centimeter and I wanted to have a scale factor of 2, 1 times 2 would be 2 centimeters. And the same could be said then for the length as well, that would also be 2 centimeters. Now, if I want to figure out the area of that square, I still do the same thing. I do length times width, which in this case is 2 times 2. And that leaves us with an area then of 4 centimeters cubed. That doesn't immediately invoke any feelings of confidence. When I look at these three numbers, when I look at 1 centimeter squared was the first area, a scale factor of 2, and then an area of 4, that doesn't really, for me, invoke any sense of like, oh, there's a pattern that exists. I have the Illuminati song going on in my background. Like, I know what's going on here. There's nothing like that existing for me. And so we're going to do two more examples, and we're going to see if we can then generate some sort of pattern. So that was the first example. Second example here. Let's just increase our square a little bit. Let's make a 2 centimeter by 2 centimeter square because sometimes ones are a little finicky with math. Again, to calculate the surface area, it's just length times width or 2 times 2, which means that this area would be 4 centimeters squared. And we'd actually solved that square already up in this top right here. Let's not do a 2 as a scale factor. Let's increase it by something a bit bigger. Let's say we want a scale factor of 3. If we do, then what that square will turn into is we need to multiply the length by 2 and also, or excuse me, by 3 and the width also by 3. So you'd end up with 6 centimeters along the top and 6 centimeters as the width. Again, all we're doing is just taking these length and width dimensions, multiplying by our scale factor, which is all we've been doing the last couple days, and then we are generating a second square. Length times width again, and you end up with 6 times 6, which means that this thing would have an area of 36 centimeters cubed. Squared. Why did I say cubed? That should be squared. So again, I see an area of the actual shape of 4 and then the area of the new shape of 36. Again, I know that like 4 goes into 36, but other than that, there doesn't seem to be much of a pattern that's going on here. Maybe some of you have identified what the actual pattern is already. And if you have, awesome, great work. But right now, me just looking at this, I don't totally see like what the pattern would be. I don't see anything that exists yet. So let's do a third one. And you know what? Instead of a square, let's do a triangle for our third one. Let's do a triangle. And with a triangle, the area of that, the surface area formula is 1/2 base times height. Let's make the height 2 centimeters. Let's choose different numbers. Let's make the height 2 centimeters. Let's make the width then 3 centimeters. So if I were to go and find my surface area of 1/2 base times height, it would be half of 3 times 2. 3 times 2 is 6. Half of that is 3 centimeters squared, would be the surface area of that triangle. Let's just increase our scale factor. Let's try a bigger number and see if that's maybe giving away any sort of pattern at all. Again, I would need to multiply both dimensions. I would need to multiply both dimensions by 4. So 3 times 4 would be 12 centimeters. 2 times 4 would be 8 centimeters. And then to find out the surface area, want to go 1/2 times 8 times 12. 8 times 12 is 96, if you remember your grade 3 times table, grade 4 times table. And then half of 96 is 48. So the surface area of that is 48 centimeters squared. Can anyone see or can anyone contribute to me what the pattern is that we've done every single time? Does anyone know what the actual pattern is that we're actually exhibiting here between the area of the actual shape and the area of the new shape? Anyone have any suggestions with that? Okay. I like seeing your faces sometimes because it actually gives me a good idea of what everyone's thinking. Um, Perfect. Okay. Well, let's think about this in this way. The original shape, and then let's compare that to the new shape. The original shape, let's think about the square that we were using. Originally, all we were doing is the length times the width, and that was how we were figuring out the surface area. With the new shape, what we're doing is we're taking whatever the length was, and we're multiplying that by the scale factor. And then what we're doing is we're also taking the width and also multiplying that by the scale factor. And so if you were to simplify this expression, because all of these things are multiplied together, we're doing length times width, and then we're multiplying by the square of the scale factor. So in essence, what we end up doing anytime we do area is we multiply by the scale factor twice, as well as just the original length times width. So that was how we ended up with this square over here. Let's look at the second example. We took 2 times 3 to get 6, 2 times 3 to get 6. So we're multiplying by this scale factor then twice when we're trying to figure out the overall area. In terms of the deductive proof, so what we want to be able to do is prove that these two statements are true. So we said that the surface area of the original was just simply length times width. Length times width. And we said that the scale factor, whatever that is, would always be equal to k. In terms of calculating the new surface area, we said what we want to do is we want to do k times the length and then multiply that by k times the width. From that, we have a common term there where we can factor out the k squared, and we're left with length times width in the brackets. And this statement here, this length times width, we've already defined that. So what we did a lot in the beginning portion of the class is we said if we can get our deductive proof to say something that we've already previously defined, that's awesome. And we had said that the length times width is equal to the surface area of the original. And so what that means is that we can say the surface area of the new object is equal to k squared. And then for length and width, I'm going to plug in the surface area of the original object. And so from that, we actually get a formula, which is surface area of the new thing is equal to k squared times the surface area of the original. So areas of similar objects are related to each other by the k factor or the scale factor k squared. Note that the scale factor must be calculated with matching units. And then one of the things that didn't get copied over when I moved this to my OneNote is this should say k squared is equal to diagram area divided by actual area. Or that should say it like that. So what we'll use this bottom little statement here for then is we'll use that statement to figure out the k. And then after we've calculated what the value of the scale factor or what the value of k is, then we can plug it back into this original equation here and then square it and multiply it by the surface area of the original. All right. Does anyone have any questions so far? No comprende? Awesome. Okay, so back to questions that look like what we did yesterday. Jasmine is making a kite from a 2 to 25 scale diagram. The area of the scale diagram is 20 centimeters squared. How much fabric will she need for her kite? So the first thing I want to do is I want to figure out K, and I'm going to do so using this above formula here. This K is equal to diagram area divided by actual area. Because I have a ratio here, what I'm going to do is set the K of 25 divided by 2, and then I get a K value of 12.5. Because I'm scaling it up, because I'm assuming that this was a drawing, I know that I want to have a scale factor or K value that is greater than 1. Then what I can do, then what I could do is I could say that the kite area, which is the new object, is going to be equal to K squared times the kite drawing. I can plug in some of my values that I know here. Kite area is equal to 12.5 squared times 20 centimeters squared. And I put a huge gap in between my centimeters and the 20 there. There is a specific reason I did that. And it is because a common problem that I noticed when I was working at Mathnasium doing some math tutoring is that a lot of people, when they see this centimeter squared here, they want to square this 20. The 20 is already a number itself. It's just the square that 2 is only being applied to the centimeter unit, meaning that it was 2 different centimeters multiplied together to get centimeter squared. So the reason I put a huge gap in between these, the number and the unit here, is just to emphasize that it's not the 20 being squared, it's the centimeters being squared. The only thing that needs to be squared is this 12.5. And when you do, and when you plug in all of your values, you get that the kite area is equal to 3,125 centimeters squared. All right. Questions, comments, concerns? Okay. Example numero dos. Jim's laptop has a monitor with the dimensions of 9 by 12, and the image on his laptop is projected onto the screen of a whiteboard. According to the documentation for the whiteboard, its screen area is 2,836.6875 inches squared. So, first thing that I would want to do looking at this question is, well, let's read A first. The image on the whiteboard is similar to the image on the laptop. Great. Determine the scale factor used to project the images on the laptop to the whiteboard. So, first thing that I see when I read that is I need to figure out the surface area, which I'm just using SA as my abbreviation, of the monitor. Presumably, sorry, that was really sloppy. Presumably, this monitor is a rectangle, like every other monitor in existence. And so we will go length times width, or 9 times 12. So length times width. And you will find that the surface area of the monitor itself is 108 inches squared. Now, here, there's a couple different things that I could do, but when I was solving this question, the way that I set it up is I said the whiteboard area is presumably the new area. So I'm taking the image from the projector and throwing that now up onto the whiteboard. And so I know that this whiteboard area will be greater than the area of the monitor. So I plugged in whiteboard area is equal to K squared, and I'd multiply that then by the monitor area. You can plug in the values that you do know. We were told the whiteboard area was 2,836.6875 is equal to K squared. We still don't know what that value is, times 108, 108 inches squared. This should be inches squared as well. I divide both sides by 108. And when you do 22836.6875 divided by 108 is equal to 26.265625 is equal to k squared. I'd take the square root of both sides to get rid of the squared symbol. And when you do, you find out that your scale factor, or the value of k, is equal to 5.125. Now, we're going to use that value then to calculate the dimensions of the whiteboard. We know that the surface area of the whiteboard is 2,836.6875 inches squared. And we also know that the whiteboard will be a rectangle, so it'll be length times width. What we don't yet know is we don't know how much longer or how much wider the objects of the whiteboard actually are. We don't know the dimensions of the whiteboard, how much longer or how much wider it is. But we do know that we have the dimensions, or we can figure out the dimensions of the monitor, and then we have the scale factor to scale that up to the whiteboard itself. So in terms of the x value, or let's call that the width of the whiteboard. What we can do is we can say, well, I know that the width of the monitor was 12 inches, and I know that the width of the whiteboard is 5.125 times bigger. So I can go 12 times 5.125, and you can solve that the width is 61.5 inches. So that's one of our solutions. And then in terms of the length, which I'll do down here, we know that the length is going to be equal to, well, 5.125 times what we found for the dimensions of the monitor, and then you get 46.125 inches for the length. So those are our two answers then for that part. Okay. I'm going to move this up just a smidge so it's out of my way. All right. So this example 3 here, we're going to use the new formula that we learned just recently. We're told the information. We had solved this exact question earlier. We had solved for k by finding out that the scale factor was 1.5. If you wanted to resolve for that, all you would do is you'd take the same side. So I'd grab the 4 and the 6, those two side lengths. You could go 6/4 and find a scale factor of 1.5. I think when we did this the first time, we did 4/6 and found a scale factor of 0.8. So that was looking at going, if I got the 0.8, that would be going from the big object to the smaller object. If I wanted to use the 1.5, that would be going from the smaller object to the bigger object. So either answer is technically correct. We weren't told what the original object was or what the new object was. So you can use either one of those two values. You just have to keep in mind what direction you're traveling. So for us, we are going to use this 1.5 value, which means we're going from big box into little box. So step A says calculate the surface area of the smaller shape. Use it to determine the surface area of the larger shape. When I was doing this, I thought of a cube, and I thought, what's a common object that I know is a cube? And I immediately thought of a little die. And then I asked myself, how many sides does a die have? Most normal ones have 6 sides. And so what that then told me is that I will need to do 6 calculations, or have 6 different solutions to be able to get the surface area of this rectangular prism. And so then what I also told myself was, I know that this side here is going to be the exact same as this back side back here. So this side that I'm shading in, it's the exact same as that back side. So I can eliminate one of my calculations by just doing that one twice. And that's true for every one of the sides. So we only need to calculate this side, and this back side here. Those are the only 3 sides that we actually need to calculate. And then we can multiply those values by 2 because there's an identical side opposite to them. So looking at this, we need 2 of this front side, which is a 4 by 5 side, a 4 by 5 side. And when you do that, 4 times 5 is 20, times 2 is 40. I then know that I need 2 of this backside here, this 2 of this 4 times 3 or 4 by 3 side. 4 times 3 is 12, times 2 is 24. And then I also know that the only side that I'm also missing here is now this 3 by 5, this top section here. And I know that I need 2 of the 3 by 5. 3 times 5 is 15, times 2 is 30. I then would add those 3 different numbers together. Again, it's like adding the surface area of all 6 sides together, and when you do, you get 94. I just got a notification we have 10 minutes left. So again, if it does boot you out, just click on the same Zoom link and it'll take you right back into this meeting. So 94, that is the the surface area of the original object, or the surface area of the smaller object. So I'm actually just going to call this surface area of smaller object. And so what I want to do now then is I want to take 94 and I want to multiply that by k squared to get the surface area of the bigger object. Again, we chose this 1.5 value for our scale factor instead of the 0.8, which means that we are doing an enlargement. We're getting bigger. So I take 94, plug in 1.5 and square that, and then we'll get the surface area of the bigger square. When you do so, you get a surface area equal to 211.5. So that's using the scale factor there to figure that out. The part B here says use the dimensions of the larger shape and just confirm the surface area. So what that wants us to do, part B wants us to redo all of this stuff that we had previously done. It wants us to redo the 2 times 4 times 5, but now with the bigger shape. So we'll do 2 times this 6 by 4.5 side, 2 times 6 times 4.5. When you do, that should be 54. And then it wants us to do the 2 by 6 by 7.5 side. So that would be 6 by 7.5 would be this side here. That one's equal to 90. And then the last thing we need to do is the 2 by 4.5 by 7.5 side. When you do, that one's 67.5. And when you add all of those numbers together, those add up to 211.5. So that would inductively then prove that this k squared value was correct. It would prove that this scale factor was correct. And it would also prove that the formula we've been using is effective in getting the exact same surface area as when we individually went through and calculated each side, added them together. Does anyone have any questions about area before we transition to volume? Cool. Let's transition to volume then. So I went through the same process of going through these scale factors. This table's slightly different, but what I did is I just borrowed that initial cube that we looked at. So the initial cube that we looked at, or the initial surface area that we looked at, was a 1 by 1 square. And so what I did this time is I said, well, let's make a 1 by 1 by 1 cube. So for us, for that question, what I did is we had set a scale factor of 2. We had figured out that the surface area of the actual object was 1 centimeter squared. So the surface area of this object, which was 1 by 1 by 1, was 1 centimeter squared. And then when we did our scale factor, when we did our scale factor of 2, we got a new square that was 2 by 2 like such. And we found that that surface area was 4 centimeters squared. So we knew that the relationship between these two was k squared. Now, the units for surface area are kind of a giveaway, and the units for volume are also kind of a giveaway. The volume formulas, oh, I didn't save that picture. I have the picture on my Google Photos. Let's see if I can pull that up real quick. Copy that, paste it there, shrink that. Okay, so here's all of our formulas. We're dealing with a rectangular prism, meaning that to find the volume, we want to go length times width times height. And in this case, it's 1 times 1 times 1, which means that the volume is equal to 1 centimeter cubed. So the volume of the object is 1 centimeter cubed. Now, if we take our scale factor of 2, we'll end up with a cube that will look like this. It will have a 2 by 2 by 2 dimensions. And so again, if we want to take the volume of the new one, we would take length times width times height and go 2 times 2 times 2, and you would get 8 centimeters cubed. Like such. So the relationship between these two, the squares, this 1 by 1 and this 2 by 2 square, was that we did k squared, and that was the relationship between the two values. Volume follows a very similar format. The relationship between these two values is, instead of it being k squared, it's just k cubed. That's the relationship between those two. So the relationship between two similar objects appears to be k cubed of the volume of the original is equal to the volume of the new. That appears to be the relationship. Now, we should probably prove that deductively. So if we take a regular cube like such, we know that the volume of this original object is going to be equal to length times width times height. Let's say that we want to scale it up by some factor of k. Well, we would need to apply that k to each and every one of the dimensions. So the volume of the new object then would be k times length times k times width times k times height. And we have a common term of k there, so we can go volume of new is equal to k cubed times length times width times height. And we've already defined that term here above. We've already said that length times width times height is equal to the volume of the original. So the formula that we get out of this is that the volume of the new object is equal to k cubed times the volume of the original object. So this deductive proof then shows us that the only thing really impacting the volumes is this k value here. And because we have three different variables we're multiplying together, that becomes a k cubed value. So volumes of similar objects are related to each other by the scale factor of k cubed. Note that the scale factor must be calculated using matching units. And again, this is the exact same formula. We'll actually use this formula in a further down example. In example 3, we'll use it. All right. Okay, so we have 2 cans of pop shown on the right. Recall that the scale factor is 1.25, and that would have been derived from going 5 divided by 4 is equal to 1.25. So taking the height of the one object, the height of the other object, dividing them out, and getting an enlargement of 1.25. So again, that would be going from the small to the bigger. What factor relates the areas of the 2 cans? What factor relates the areas of the 2 cans? So this one's talking specifically about the areas. So what we'd want to do then is take the scale factor and square that. And when you do, you get 1.5625. Next question says, what factor would relate the volumes? Well, volume always deals with units in cubed, and so our scale factor also needs to be cubed. And so 1.25 to the power of 3 is 1.953125. So those are our scale factors for comparing. I'm seeing we have less than a minute. So before I jump into example 2 and get cut off, I'm going to just close the Zoom call. There you go. Start. Welcome back, Heidi. Glad you made it. Glad you figured it out. Brooklyn, I like that painting or mural that's behind you. It's awesome. Everyone figured it out. You guys are so tech savvy and just wonderful. The one thing I'm realizing I don't like about Zoom calls is I have my 2 monitors set up, and it makes me look, because I have 2 white screens shining at me, makes me look extremely white. It's just what I'm realizing. It makes me look very ghostly. I'll have to work on my tan and get that figured out. All right. Did we lose anyone? I think we have everyone back. So that's great. Okay. Let's jump into this the second example then here. So we have the Great Pyramid in Egypt. I'm going to draw my first rendition in my little notes was really, really bad. So let's see how this goes. Here's a pyramid. Yep, just about as bad as the other one. And then here's the little Sphinx that likes to sit there. I'm going to give him a couple whiskers. There's the Sphinx. Looks like a cat on a rollerblade or skateboard or something. Anyways, what scale factor is being used to build the model? So what we want to look at here is we want to look at the different values that we've been given. The Great Pyramid in Egypt has a base width of 228 meters. I'm going to call this one the original object because my guess is before this model was ever built, the pyramid was probably built. A model is going to be built with a base width of 4.0 meters. So using our K value, we always use the diagram over the actual. So in this case, we're going to go the diagram width over the model. Diagram width over the actual width. So plugging in those values, we have the diagram width of 4.0 meters. And the original huge pyramid has a width of 228 meters. And when you divide those out, you get a K or a scale factor of 0.0175. And that value makes a lot of sense because we're going from a huge pyramid to a super, super small model. And actually a 4-meter width, that's actually not even that small of a model now that I think about it. That's like me laying down twice. That's like 2 full meters or 2 full me's. So that's our K value then that we're going to be using for the rest of this question. That's a very important value to us. The surface area of the Great Pyramid is 84,998.4 meters squared. What will the surface area of the model be? So what I'm going to do here is I'm going to take this 84,998.4 meters squared. I'm going to multiply that by k squared, and then I'm going to get the surface area of the new object, or surface area of the model. So we get 84, 9,998.4 meters squared. Multiply that by 0.0175, and we need to square that value. Again, reminder that this meters squared does not mean that the 84,000 is also squared. It just means that the meters have been squared. When you do so, you end up getting a new surface area of 26.03 meters squared as our final solution. And that looks like a 3. Let's fix that. Meters squared. Okay. The next question, presumably and obviously, jumps into the question of volume. The Great Pyramid was built with 2,540,284.8 meters cubed of rock. That is a lot of rock. So what we will do then is we'll say that the volume of the original times k cubed must be equal to the volume of the new. And we can plug in all of our values. The 2,540,284.8 meters cubed. We want to multiply that by 0.0175 cubed. And that'll equal the volume new. We then find out that 13.614 meters cubed is equal to the new volume. So those are our 2 solutions for number 3 then. Does anyone have any questions at this point before we jump into the final example here? Okay. Spherical tank, that gets a little, I don't even know what grade. Probably grade 7, Mr. Nickel. That gets him really excited because he sees a sphere and he immediately knows that it's 4 pi r cubed. And he gets super excited that it's the only volume formula he will ever remember for the rest of his life for some odd reason. But it has a capacity or volume that it can hold of 1,400 meters cubed. A larger tank has a capacity of 4,725 meters cubed. The first question that we're asked is how many times longer will it take to fill the larger tank? And for that, what I'd like to know is I'd like to know what the K value is for this. I want to know how much bigger the one tank is as compared to the other. And so what I'm going to do is I'm going to take the volume of the larger and I'm going to divide that by the volume of the smaller. And whatever that value is, whatever that comparison is, I'm in essence setting up a fraction or a ratio to figure out the scale factor value, and that will communicate how many times bigger something is than something else. And in theory, will also let me calculate how much more time it will take to fill up as well. So plugging in our values, 4,725 over 1,400. And I guess I can put my units here, but because we have a meters cubed up top and on the bottom of our fraction, those will cancel out. And we end up with a scale factor of 3.375. So if I were to write a sentence, it'll take more than 3 times longer to fill the larger tank. Okay, so all that question was a convoluted way of asking you what is your scale factor. The next question here says how many times greater is the radius of the larger tank than the radius of the smaller tank? If we were dealing with another object, this question would be more difficult. So if we were dealing with a cube, this question would be more difficult, or a rectangular prism, I guess, because we would have to also take into consideration the length, width, and height. Because we're dealing with a sphere, and this is where all of this must be the reason that I remember what a sphere is. All of my knowledge up until this point has led me to this moment. But a sphere, I know the only variable that is actually changeable in the volume formula is the radius. And so now I can only look at the radius. I get that exclusivity of only considering the radius and how that dimension can change. It's the only dimension that impacts the volume. So what I would do is put the volume of the larger in and say that that must be equal to k cubed times the volume of the smaller. Again, we have a positive k value here. A value's above 1, so that means that this is an enlargement value. So we want to put the k cubed on the side of the smaller object then. So volume of larger, this was 4,725. We said that that's equal to k cubed times 1,400. I would divide both sides in this case by 1,400 because I want to solve for k cubed. And then what I would do is find out that I've already done this division before. 3.375 is equal to k cubed. We then take the cube root of both sides because this is cubed and we want to get rid of that to solve just for k. And you'd find out that the radius of the larger tank was 1.5 times longer than the smaller tank. The radius of the larger tank is 1.5 times longer than the radius of the small tank. All right. Does anyone have any questions, comments, concerns about proportional reasoning? Proportional reasoning. That was a hard word to say today. If not, that's awesome, and I hope it was a unit that you enjoyed. We get to transition into statistics next week, which I am super pumped about. I personally love statistics. I base a lot of my decisions in life and also in teaching as well around statistics. So all of the things that I do in the classroom are based off of statistics. I think that stats are a very reliable, often way of communicating information and also saying like what works better or how well you're doing in some aspect or another. So I'm excited to look at it. We will also spend a week. Like I said, I've been saving a bunch of one of my professor's posts about COVID-19. So we'll spend a week looking at the stats of COVID-19. And because I also got to go through health sciences with all of you, we'll also integrate and bring in some of those aspects as well when we talk about transmission ratios or when we talk about